Have you ever wondered how that shiny gold ring on your finger or the gleaming bars in a bank vault came to be? The journey of gold is a fascinating, complex, and fiery one, transforming ordinary-looking rock into pure, precious metal. Today, we're going deep inside a modern gold refining plant to uncover every single step of this incredible process. So let's get started on this golden adventure. The story of gold begins long before it reaches a refinery. It starts deep underground or in colossal open-pit mines. The raw material, gold ore, is surprisingly unassuming. It's just rock, gray or brownish, that contains microscopic traces of gold. We're talking about incredibly small amounts, sometimes just a few grams of gold for every ton of rock. To get it, miners use powerful explosives and massive machinery, giant drills and haul trucks to blast and transport the ore. When you look at a pile of this rock, you'd never guess it holds one of the most coveted metals on Earth. Once extracted, this ore is loaded up and sent to the refining plant, which is where the real magic happens. The first stop inside the plant is all about brute force, crushing. The huge chunks of ore are fed into massive machines called jaw crushers and cone crushers. Their job is to break down these big rocks into smaller, more manageable pieces about the size of gravel. But that's not nearly small enough. The gravel-sized ore then moves into giant rotating cylinders called mills. These are often ball mills or sag mills, and they're filled with heavy steel balls. As the mills spin, the steel balls tumble and grind the ore, smashing it into a fine powdery dust, similar in texture to flour. During this grinding process, water is added to create a wet, flowing mixture known as a slurry. Why go to all this trouble? Because the tiny, microscopic gold particles are trapped inside the rock. Grinding is the crucial step that liberates them, making them accessible for the next stage. With the gold particles freed, the next challenge is to separate them from all the worthless rock dust. This is where some clever chemistry comes into play, a process called flotation. The slurry is pumped into huge tanks, and special chemicals, known as collectors, are added. These chemicals have a unique property. They attach themselves to the gold and other valuable sulfide minerals, making them hydrophobic, meaning they repel water. Instead, they prefer to stick to air bubbles. Air is then pumped vigorously through the tanks, creating a frothy layer of bubbles on the surface. The gold-bearing particles hitch a ride on these bubbles and float to the top, forming a thick, bubbly froth. This froth is then carefully skimmed off. The waste rock, which doesn't stick to the bubbles, simply sinks to the bottom. This flotation process is incredibly effective. The skimmed froth, now called a concentrate, is already 10 to 30 times richer in gold than the original ore we started with. Now, many gold ores have a common companion: sulfur. And sulfur can interfere with the next, most important step of gold extraction. So before we can get to the gold, we have to get rid of the sulfur. One common method is called roasting. The concentrate is heated in massive furnaces to scorching temperatures, over 600 degrees Celsius, while being blasted with oxygen. This intense heat burns off the sulfur, which is released as sulfur dioxide gas. What's left behind is a porous, crumbly material called calcine, where the gold is now exposed and ready for extraction. An alternative, more high-tech method is pressure oxidation. Here, the concentrate is treated with oxygen in a sealed, high-pressure vessel called an autoclave. This also effectively removes the sulfur and prepares the gold for the next stage. This brings us to the heart of the gold refining process: leaching with cyanide. Don't worry, this is done under extremely controlled and safe conditions. The calcine, or treated concentrate, is moved into large tanks and mixed with a very weak solution of sodium cyanide. Cyanide has a remarkable chemical affinity for gold. It latches onto the gold particles and dissolves them, pulling them out of the solid material and into the liquid solution. This forms a chemical compound called a gold cyanide complex. To speed up this reaction, air or pure oxygen is continuously bubbled through the tanks. The entire leaching process can take anywhere from 24 to 72 hours. At the end, we have two things: a liquid called the pregnant solution, which is now rich with dissolved gold, and the leftover solid waste, known as tailings. These tailings are carefully managed and detoxified to ensure they don't harm the environment, so now we have all our gold dissolved in a liquid. How do we get it back out? The most common method uses activated carbon. The pregnant solution is passed through a series of large columns packed with granules of activated carbon. Activated carbon is like a magnet for gold. As the solution flows through, the gold cyanide complexes stick firmly to the surface of the carbon granules. This process is called adsorption. After the carbon is fully loaded with gold, it's moved to a separate vessel. Here, it's washed with a hot, caustic solution which reverses the process, stripping the gold off the carbon and back into a new, much more concentrated liquid. An older but still used method, especially for ores with high silver content, is the Merrill-Crowe process. Instead of carbon, zinc dust is added to the pregnant solution. The zinc causes the gold and silver to precipitate, or fall out of the solution as a solid sludge. Whether from carbon stripping or zinc precipitation, we now have a highly concentrated gold product. This is filtered and dried into a powder, then mixed with special chemicals called fluxes, like borax and soda ash. These fluxes help separate the last remaining impurities. The entire mixture is then loaded into a crucible and placed inside a smelting furnace, where it's heated to a blistering 1,200 degrees Celsius. At this temperature, everything melts. The impurities react with the fluxes to form a molten, glassy waste called slag. Being lighter, the slag floats to the top and is carefully skimmed off. What's left at the bottom is pure, molten gold. This liquid gold is then poured into molds to cool. The result is a rough, unrefined bar called a doré bar. These bars look golden, but they're not pure yet. Typically they're about 80 to 90% gold, with the rest being silver and other trace metals. To get closer to pure gold, these doré bars undergo another round of refining, often using the Miller process. The bars are remelted in a special furnace, and pure chlorine gas is bubbled through the molten metal. Chlorine reacts with most of the remaining impurities, like base metals and silver, forming chlorides. These chlorides are less dense and rise to the surface as another layer of slag, which is then removed. This process is very effective at getting rid of silver and can produce gold that is about 99.5% pure. This is already very high-grade gold, but for financial markets and high-tech applications, we need to go even purer. For the absolute highest purity, we turn to electrolytic refining, also known as the Wohlwill process. This is the final and most precise step. The 99.5% pure gold bar from the Miller process is used as the anode, the positive electrode in an electrolytic cell. This cell is filled with a solution of gold chloride. The cathode, or negative electrode, is a thin sheet of ultrapure gold. When a powerful electric current is passed through the cell, an amazing thing happens. Gold atoms from the anode dissolve into the solution, travel across, and plate themselves onto the pure gold cathode, one atom at a time. The gold deposits as beautiful, ultra-pure crystals. Any final trace impurities, like platinum or palladium, either stay dissolved in the solution or fall to the bottom of the cell as a sludge, which itself is collected to recover those other precious metals. Finally, we have our ultra-pure gold, typically 99.99% pure or even better. These pure gold crystals from the cathode are carefully collected, washed, and dried. They are then melted one last time in an induction furnace at over 1,060 degrees Celsius. The brilliant molten liquid is then carefully poured into precision-molded graphite molds. Once it cools and solidifies, what emerges is a gleaming, perfect gold bar. These are often the iconic 400-ounce good delivery bars used by central banks and traded on international markets. Each bar is meticulously weighed and then stamped with its exact weight, its purity, the refiner's official mark, and a unique serial number for tracking. And there you have it. From tons of dull, ordinary rock containing just a few grams of hidden treasure through a multi-stage journey of crushing, grinding, floating, roasting, leaching, and intense purification, we've created a bar of pure 24-karat gold. It's a testament to incredible engineering, chemistry, and metallurgy. The next time you see a piece of gold, you'll know the amazing story behind it. Thanks so much for watching, and if you found this journey as fascinating as I did, don't forget to like, subscribe, and hit that notification bell for more deep dives into how our world works. See you in the next one.